Hello, this is Ariel NY4G, hoping to provide another useful insight on how to use a Nano VNA to measure the efficiency of an end-fed half-wave transformer. End-fed half-wave antennas are a favorite among portable operators. It is also very popular as a stealth antenna in antenna-restrictive environments, such as those in HOAs with CCR restrictions. They are favored by portable operators because they don't need an impedance matching device because they are typically resonant for specific frequencies or bands that they're designed for. And so for the portable operator, it's one less piece of equipment that needed to be carried. Also, some very popular radios such as the FT817, the ICOM 705, or the Mountain Topper series of radios do not have a built-in tuner. They are also very easy and less troublesome to deploy in the field. However, with all these advantages, there are also some shortcomings, and one is the power limitation by the transformer core size. If you have a small core, it can only handle so much power. And of course, when you have a transformer type of device, there is some power lost in the transformer itself. And the question is just how much is lost in the transformer. Hence the need for a vector network analyzer, or a VNA. Let's go over some antenna system basics. Where does all the power go in an antenna system? We can group these, or we can describe these little buckets where power goes in terms of resistance. One of those is called the radiation resistance. And this is the good resistance. You want this to be the maximum. And this is the resistance that arises from radiation of the RF with the wire. And then there's conductive resistance, which is the I²R heating of the wire. And there's ground resistance, which are losses to ground. There's reflection losses, which will be lost in a lossy feed line, and those reflection losses are arising from a mismatch between the impedance of the radio and the impedance of the antenna system. Of course, there's transformer losses when using a transformer, and if you are using an impedance matching device such as an ATU or antenna tuner unit, then there are some losses associated with that. Although mostly applied to quarter-wave verticals with a ground system, even half-wave wires have some sort of ground image loss, especially when they're near the ground or when they're low to the ground. These ground image losses are minimized when the half-wave wire is greater than about a half a wavelength above the ground. For simplicity's sake and for this exercise, we will lump the radiation resistance, conductive resistance, and ground resistance as a single resistance. So what we will need is a Nano VNA, which we can purchase from Amazon or other retailers. And typically these are sold with port extenders. And they're also sold typically with calibration standards. And the calibration standards are an open, a short, something that facilitates a through measurement, and a load, which is typically a 50 ohm load. You will also need a set of SMA to something that will connect to your antenna, either a BNC or a PLA 259 type of adapter. And the easiest one to use is a BNC, an SMA to BNC adapter. And you'll need both the male and female parts of it. We will also need a set of resistors that will equal the impedance of the antenna that we're trying to mimic. And typically the impedance at the ends of a half-wave wire are high, and we're trying to transform that high impedance into a 50 ohm impedance. And so if we're trying to simulate a 64-to-1 impedance transformation, that'll be 64 times 50, or 3200 ohms. If we're trying to mimic a 49-to-1 impedance transformation, that's a 2450 ohm resistance. So we assemble everything that's needed, and then we're ready to do some measurements. We'll try to explore two methods. One is called the resistor method, which I mentioned before, and uses a resistor to simulate the antenna. And the second one is called the back-to-back method. It uses two identical transformers that are connected back-to-back and then connected to the NanoVNA, such that the loss from both can be divided in two, and you get the loss of one is just half the total loss. It's not really as simple as it sounds, but we'll explore that too. Here's a picture of a NanoVNA with ports 1 and port 2. Port 1 is this port that's above port 1, and this port 2 is the port below. This is called the reflection port. Port 1 is also known as the reflection port, and port 2 is also known as the transmission port. And this is typically a touch screen, and you can display the S parameters by touching the screen and choosing how to display them. In this case, in this picture, the S parameters are being displayed by 4 traces: a yellow trace, a green trace, a sort of a blue trace, and a purple trace. The green trace is a Smith chart, and the yellow trace is log magnitude of the port 1 parameter. This blue trace is the log magnitude of the S21 parameter, and the purple trace here is the delay, or no, it's the phase of the S21 parameter. So we can display as many as 4 traces on a NanoVNA. So different ways that you can display them are listed here: log magnitude, standing wave ratio, a Smith chart, phase, delay, the real part of the impedance, the imaginary part of the impedance, and much more. But in this presentation, we will mostly or mainly focus on log magnitude and a standing wave ratio, SWR. Now, this is a chart that sort of graphically depicts loss and gain in logarithms. So the y-axis is in logarithm from 1 to 10, and from 1 to a 10th. And so it's logarithmic on the y-axis and linear on the x-axis. So this is a linear scale here. It goes from 0, 1, 2, 3, 4. And as you can see, the intervals get smaller and smaller as you go up higher in intervals, and gets larger and larger as you go lower. So a 1 dB loss, for example, is about right here. And that's about 20% loss in signal strength. a half a dB is right here, and it's about 10% loss in signal strength. And likewise, a 3 dB loss is about half your signal strength is lost, because now you're down to 0.5, 0.1, 0.2, 0.3, 0.4, and 0.5. And likewise, if it's 3 dB gain, you've doubled your signal, and that's going from 1 to 2. So this is sort of a calibration of your brain to get familiarized with the logarithmic scale that you're typically going to be dealing with. On this next chart is the standing wave ratio, or in the power loss associated with standing wave ratio. So the S11 parameter is minus 60. That's a standing wave ratio is 1, which we typically say is a good standing wave ratio, because there's no power, there's no reflection loss going back to the radio, and everything is being transferred, energy is being transferred to the antenna system. So the reflected power is 0. Contrast that with an S11 of, let's say, minus 9, and so your standing wave ratio is now closer to 2, and your reflected power is about 12%. So this is just another calibration chart, so you know what these numbers mean, because what you will be plotting or calculating in your spreadsheet and using in your spreadsheet are the S11 and S21 parameters. The first thing we will do is calibrate the Nano VNA, and you'll use the standards. You connect your port extenders, and you'll put an open standard at the end of your port, and it's easiest depicted on a Smith chart. And an open on the Smith chart is a marker at the very right end of this line. So that's an open. And then the next thing is to calibrate with a short. And on the Smith chart, it will go to the left extreme of this line. And here's the short standard. And next, we will calibrate with the load standard, the 50 ohm load standard, and the trace will now go to the middle. And then last is we'll connect the port extenders together, so there's a through connection between S11 and S21. And on the Smith chart, this marker will stay in the middle. And when you're all done with the calibration, you click Done, and then save the configuration in your Nano VNA. So what we will do first is assemble for the resistor method. And we've calibrated Nano VNA with the calibration plane being the terminations of the port extenders, where you have the BNC connectors. We soldered the resistors together into a string, and the sum of the resistances should be equivalent to what we're trying to simulate as an antenna. So if we're trying to simulate the 64:1 impedance transformation, we'll choose resistors that add up to 3200 ohms. If we're doing a 49:1, we'll choose the resistors that add up to 2450 ohms. So we connect one end of the resistor to the antenna port of the end-fed half-wave transformer. We connect the female end of your port extender to the male BNC connector of the end-fed half-wave transformer, so that you form a loop between S11 port and S21 port. in a manner like this. So there's the S11 port, the port extender connecting to the BNC connector in your transformer. The one end of the resistor is connected to the antenna port on the transformer, and the other end is connected to the S21 port via the port extender. So here's just a collection of port extenders, the resistors, and the calibration standards. So we connect everything and we're ready to make some measurements. And we set up the NanoVNA for 3 traces. We'll have a trace for channel 0 in this case, or port 1, or channel 1, and depending on what kind of NanoVNA you purchase, it'll indicate either channel 0 or channel 1, or channel 1 will become channel 2. So just to differentiate between these two. The one I have has channel 0 and channel 1, so I have to be careful to say S11 is associated with channel 0 and S21 is associated with channel 1. So the third trace we set up, the second trace we set up is the S11 standing wave ratio, which is the blue trace. That's this trace here. And then the last trace we set up is the S21 trace, which is the log magnitude of the, that's the green trace actually. Not, that indicates blue. I think I copied it and made a mistake there. And then the stimulus we set up between 3 megahertz and 30 megahertz. And we'll have markers for each trace as we sweep the frequency from the low end to the high end. And the marker will move as the frequency changes. Here's the block diagram of the resistor method, and this is your block diagram of a radio, a feed line, a transformer, and an antenna wire. And some of that power is radiated, some of that power is dissipated in the wire, I-squared heating of the wire, and some power will be lost in the transformer. Some power will be reflected if there's a mismatch between the impedance of the radio and the impedance of the antenna system. So S11 is the log magnitude, is typically a large negative number. It's the power received in port 1 based on the input in port 1. And S21 is the power received at port 2 relative to the power input at port 1. And here's another block diagram showing the NanoVNA. We've eliminated the feed line, and we just have the transformer and the resistor. So if we set, if we imagine that the incident power is 1 watt, the through power that goes through is the incident power minus any reflected power. Here's the block diagram with that feed line omitted. S11, power received at port 1 compared to power input at power input into port 1. S21 is the power received at port 2 compared to the power input into port 1. And so the losses we'll have a mismatch loss, transformer loss, and the resistor loss. And the transmitted power is the difference between the through power and the power that's consumed in the transformer. So, so 2 ways to bookkeep. You can bookkeep it in terms of power, or you can bookkeep it in terms of loss in dB. We'll use the first method and then check the answer with the second to make sure we're getting the same answer both ways. So the transformer efficiency is the through power minus the transformer power divided by the incident power minus the reflected power. And that's we'll calculate all of that in some sort of spreadsheet. So S21 is the transmission loss, and it's equal to the insertion loss plus the resistor loss. If I use that 3200 ohm nominal resistor and actually measures out to be 3182 ohms, I can actually use the actual value and calculate what that loss is in terms of the transformation ratio, 3182 divided by 50, take the log of that, log 10 of that, and multiply it by 10, and I'll get a number of dB. The dB loss associated with that resistor is minus 18.04. If I actually measure an S21 or a transmission loss of minus 18.36, then the insertion loss is the difference between the S21 and once you deduct the resistor loss, that is your insertion loss at, let's say you're measuring it at 3.54 megahertz. The transmitted power is the anti-log of the insertion loss divided by 10, and it'll be a number like 0.93, and the efficiency, which is the transmitted power, will be that 93 divided by the through power, which is the incident power minus the reflected power, and that's the efficiency of the transformer at that frequency. So that's one way of calculating the efficiency. So we calculate all that in a spreadsheet, and we can make a table of the efficiency of the transformer as a function of frequency. So this is the different frequencies. We sweep all the way up from 3.5 megahertz all the way out to 28 megahertz. Each one of these is an amateur radio band, and we calculate the transformer efficiency using this column here. And once we have the numbers all calculated, we can plot them using Excel, either in terms of efficiency, which is in percent, or in terms of loss, which is in dB. So the loss is like a little bit over a quarter dB here at near 20 meters, 14 megahertz, and it sort of increases into about a little bit over a half a dB at the high end. And this is the other way to calculate the transformer efficiency, which is to compute the transformer loss, which is the insertion loss minus the mismatch loss. The mismatch loss is 10 to the log 10 of 1 over the through power. So this will give us a number like minus 0.0102 dB. And the transformer loss is then just the difference between that insertion loss minus a number, which will be a number like 0.31 dB. And as you can see, once we take the anti-log of that transformer loss, we get the same answer as before. Now let's set up for the back-to-back method. We calibrate our Nano VNA like before. We use the same calibration. We attach port 1, the S11 port, to the BNC connector of one transformer, and port 2, the S21 port, to the BNC connector of the second transformer. And then we have a shorting jumper between the two antenna ports of both transformers. And so we form a loop from Nano VNA S11 port to the S21 port, like so. There's the Nano VNA S11 connected transformer BNC, S21 connected the second transformer BNC, and a shorting jumper in between. There's the block diagram of the back-to-back method, and the transformer loss is the insertion loss divided by 2 minus the mismatch loss. And we compute the mismatch loss the same way we did before, which is related to the through power, so it's 10 to the log 10 of 1 over the through power, which gives us a number like minus 0.05 dB. The transformer loss is, we would take this number and divide it by 2 because there's 2 of them. And then we take the difference, we deduct the mismatch loss, and we get a number like 0.38 dB, and we get a number closer to 91%. And we can plot the same numbers again, and we're getting about a something over 90% efficiency here in terms of efficiency, and about 0.4 dB in the middle here in terms of loss. Close but slightly different results, and it's because these two methods give slightly different answers, but the answers are in the same ballpark. Now let's look at, in a real antenna system, you'll be using a feed line, and depending on what feed line you use, you can lose power in the feed line as well because of coaxial cable losses. And these losses are a function of frequency of the input. The higher the frequency, the greater the loss per 100 feet. And these are all tabulated as loss per 100 feet. And I showed this to illustrate that if you have a center-fed dipole with a long feed line, you can actually have more loss in your antenna system using a dipole with a long feed line as opposed to an end-fed half wave with an efficient transformer and a short feed line. So, other things being equal, the end-fed half wave can outperform a center-fed dipole. So what really matters for efficient transformers? It's choice of the core that you have. Typically, one would use some sort of an FT140 or an FT240 type core with a 43 mix ferrite. But you can also get these other products with a different designation. This one is called 264-325-1002. And if you compute the surface to volume ratio, it has less surface to volume ratio than the FT140 series of, or the FT series of ferrites. And that seems to help the efficiency quite a bit. So typically we use a 43 mix. The way it is wound, if you wind it tightly around the core, it helps the efficiency. The number of primary turns is also important. Although the more primary turns you use, it makes it harder to to match with the ham bands, and there's also typically an efficiency fall off at the higher frequencies that are not present when you only use 2 primary turns. And in the DIY world, or the do-it-yourself world on the internet, you have a lot of examples of inefficient designs because the designs were not really computed to be for efficiency, but more computed for impedance matching. So here's an example of an inefficient transformer. You can see that the windings are not tight. And there's typically a crossover in the secondary. So you'll wind the 2 primaries here, go this way, and then cross over, and then keep going until you terminate to the antenna connection right here. This is typically what one could purchase or make. Here's another one. This is a commercial antenna product by myantennas.com, and it happens to be an efficient one. And they actually publish on their website what the dB loss is as a function of frequency, and it's typically in the order of like 0.4 dB, and it's reasonably flat. There's not a fall off at the higher frequency, which is good. Here's another efficient transformer. This one is, I measured, I don't think that they have published literature that actually show the efficiency, but I measured it using a NanoVNA, and it's just around 90%, and it's flat across the bands. Here's another example of an efficient transformer. This is a 2-stack of FT140-43. It's wound tightly, like I mentioned before, and it gets over 90% efficiency, and it's reasonably flat across the bands. And this is the dB loss in dB as a function of frequency, typically around 0.4 to 0.45 dB. Right at 20 megahertz, at 14 megahertz, 20 meters. Here's another example of an efficient transformer, wound tight again, but this one uses the ferrite 264-325-1002, and it's a more massive core, dissipate a lot of heat, and this typically is up in the higher 90s in terms of efficiency, and dB loss is closer to the 0.15, 0.2 dB as a function of frequency. And lastly, this is the QRP version of that 264-1002, and this is the designation 264-362-5002. It's a much smaller core, and it's meant for QRP use, and it's also in the high 90s in terms of efficiency. So the key takeaways is that you do not wind your transformers like the suggestions on some of the internet websites that have no idea how much power is being wasted. Although impedance matching is important, efficiency is also important. So you try to balance between the two, and so you try to have a good impedance match on your antenna and also maintain an efficient transformer. And there's a blogger on the internet by the name of Owen Duffy, and he says in his blog, in ham radio everything works, but systems that work better increase the prospect of contacts.